Welcome everyone. Today we will present proof of concept dynamic model of Koniambo Ferronickel's Ladle Refinery using ChemApp and M4D-GCI library. Our co-authors are Nicolas Lazar from XPS and Karim El Kayar from Koniambo Nickel SES. Presenting with me today is Munir Baitej, process simulation developer at XPS. My name is Tanai Marin, former manager of process simulation and modeling group at XPS. We will start our presentation by providing a high-level introduction and objectives of this project and model, followed by a brief description of the ferronickel refining process at KNS. Then we will discuss the modeling approach and discussion of the results, to finalize with the summary, conclusions, and next steps. The main objective is to develop an application to simulate ferronickel refining step at KNS, focusing mainly in accurately predicting the sulfur concentration during refining. In order to do this, an offline thermodynamic-based model was built as a proof of concept, and the model is capable of reproducing the data from past gas and estimate the temperature and composition of the system as a function of time. To do this, a custom-made thermodynamic system, including a liquid metal phase, slag, reagents, and rivets, was created using XPS in-house database. The proof of concept is based on Excel, where the plant data is read and input to the ChemApp model using XPS's M4D-GCI library. At this stage of the project, the purpose is to evaluate whether the offline model can predict the behavior of the refinery process and to use plant data to calibrate the model parameters. The case consists in refining of ferronickel in a ladle furnace. During the process, the metal before treatment is analyzed to determine the initial chemical composition and determine the amount of batches of reagents needed to reduce impurities. The liquid metal is treated with or without a quantity of recycled metal or alloy, rivets. The reactants are added to the ladle furnace following gas stirring and heating procedures. All the steps are considered in the form of time-dependent streams in the thermodynamic model. The model is built according to the system of components and constituents verified in different partial equilibrium at different temperature regions. The details of the constituents will be present in the section related to the input files. This schematic shows the relation between the input streams and equilibrium conditions used for the model. The model starts by adding a liquid metal phase at typically 1450 degrees centigrade, with a chemical composition containing several elements, such as sulfur, silicon, carbon, phosphorus, nickel, aluminum, iron, copper, cobalt, manganese, chrome, and zinc. Initially, in the ladle, a set of rivets at 1100 degrees centigrade can be present, with varying composition representing a solidified metal alloy. Once the ladle is filled, then several streams are used during the refining, starting with aluminum, which is used for deoxidation, followed by a set of different reagents composed of ferrosilicon, lime, dolomite, spath to complete the refining process. The constituents of all of those reagents is shown in this slide. Other streams are also considered, such as carbon, which arises from the consumption of the electrodes during heating, nitrogen, which is used for stirring, and oxygen as infiltration. Then the equilibrium conditions set for the model correspond to enthalpy mode, where an enthalpy target is calculated based on the heating input recorded by the plant data and the estimated heat losses. To finalize, the model predicts or calculates the desulfurized or refined ferronickel plus the slag phase.
So in order to build a reliable thermodynamic model, the steps we followed are first, develop the thermodynamic database with the necessary constituents and phases, link the database with the GCI library, and finally develop the user interface, as in our case, an Excel interface. Then comes the stage of evaluating how the model performs according to the input data that comes from the industrial process. The step that is presented by these results in this slide is the calibration of the heat loss. The heat losses are of big importance in order to calculate with great accuracy the enthalpy of the thermodynamic system. To determine realistic value of this heat loss in the process, different simulation sets were run by testing different values of heat fluxes and comparing the results with the temperature recorded in the liquid metal. At the end of those simulations, we were able to set an overall value which was applied in the model. As it can be seen or observed in these results, a value around 2.2 megawatts of heat losses makes it possible to reach in the system at different times the same values of the measured temperature. Next slide, please. The results shown in this slide summarize the heat balance, including the energy supply during the heating cycle, the heat losses, the transient temperature calculated by the model, and the values of the temperature measured in the liquid metal. These results were obtained by considering 2.2 megawatt, as I mentioned before, of losses. And in the results that follow, all casts have been simulated with the same value. Next slide, please. The calibrated model was applied to more than 15 ferronickel refining casts with process data recorded by the plant acquisition system, PI. All the simulations gave results which agree with the measurements. An example of the results is shown in the graphs of this slide. We can see the results of the heat balance and the mass and that of the mass balance as a function of time during the whole desulfurization process. The measured and predicted temperatures show that the model give a very good estimate of the system enthalpy. The mass balance demonstrates that the principle of the mass conservation is well respected and predicts the appearance of the phases during the progress of all the process. Next slide, please. The results here show the calculations by the model of the time-dependent sulfur content. The successive decreases of the sulfur percentage correspond to the times when the reagents are added, in particular the lime. In the histogram of the right-hand side, we see the comparison of the measured and those calculated by the model of the sulfur content. The first value shows a relatively large difference. This can be explained by the partial solidification of the metal when the first batches of reagents are added, which are at low temperature and before starting the first heating phase. The quantity of sulfur that is presented is calculated in the liquid phase. Next slide, please. The silicon content is presented in these graphs and is compared with the measurements of the metal samples. The source of silicon is ferrosilicon that is added to deoxygenate the liquid metal. The calculated final content is very close to the measurements of metal samples in the plant. Next slide, please. The prediction results of another cast are presented in the following. We can appreciate the relatively small differences between the predicted temperatures by the model and those measured in the liquid metal. We see that the same realistic mass balance behavior as expected from the model is obtained. And in the temperature graphs, we can see, or histograms, we can see that relatively the differences are acceptable. Next slide, please. The comparison was carried out for all the casts, the 15 casts we performed, and by the model we can see that also in this example we can see that the final sulfur content is almost the same as in the measurements. And in the next slide, we can still see that for this example, the results of silicon content are also very similar to the measurements. And as summary, next slide for you.
So to summarize, the input plan data must be adjusted or was adjusted to be formatted manually so that the model can read as a script from the Excel interface. More measurements must be taken during the process and further automate the acquisition of information to avoid missing data and recalibrate the model dynamically. More importantly, the model is capable of predicting the desulfurization process. And finally, the model can be converted to an online digital twin model in the future, allowing KNS to use it as a decision-making application. Thank you very much for your attention, and please don't hesitate to contact us if you have any further questions.